So this session is titled No Single Point of Failure, and it's about high availability. High availability is a characteristic of a system which aims to ensure an agreed level of operational performance, usually uptime, for higher than a normal period. Basically, your application keeps on running, not necessarily 100% of the time, but it keeps on running more than what people currently expect it to run. Then it's high availability as opposed to normal availability. So how many nines does it take? Or rather, how many hours or minutes or milliseconds do you get to be down for various levels of 9 guarantees? So 55.55555559 fives of uptime, you can be down for 162 days. That's pretty easy to do, hopefully. I think you can maintain more uptime than that, probably. If you guarantee 90% uptime, you get to be down for 36 days. So that's a lot of downtime. Probably can do better than that. 95 is 18 days, and it starts to accelerate pretty fast as we get farther and farther down the nines list until we make it down to 8 nines where we're sub a second for a year. So that would be really hard, right? Like any kind of hiccups start adding up onto that milliseconds list or that seconds list, and all of a sudden it gets really, really hard to actually meet that guarantee. So if your salespeople find themselves offering 9 nines or anything probably more than about 5 nines of guarantee, you might want to question their sanity just a little bit. Scale that one back into the 3 nines 5 or the 3 nines area, because those are achievable with a lot of effort, but they are actually achievable. And I'm going to talk about some of the ways you can do that. What are the building blocks of getting those nines? Eliminations of single points of failure. So if you have all of your data stored on a single hard disk array, that's a single point of failure. If anything goes wrong with that thing, you're down. How long? Don't know. Depends on your backup strategy, whether you have another piece of comparable hardware that you can replace it with to load those backups back onto, but it is a single point. If it goes down, you go down. The other big part is reliable crossover. So if I don't have a single point of failure, how do I make sure that if group of hardware A fails, I stop using group of hardware A, and instead all the users end up on group of hardware B? So if there's not a reliable way to determine this is alive and functioning properly, that causes downtime, because I don't know where to send people. And along with that reliable crossover, you have to know that stuff has failed. If you don't know stuff has failed, no crossover. It doesn't matter that you had no single point of failure. People experience downtime. Like 50% of your users are now experiencing downtime because they're still hitting the dead part of your environment. So you have to detect the failures, crossover, and don't have single things. Why do we want it? Because downtime costs money, like a lot of money. When your software is not processing transactions, you're not making money, or your customers are not making money, and then they get angry at you for their lack of making money, and they impinge on your ability to make money. So downtime is bad. Customers are asking for it. They're getting used to this whole high availability thing happening because the cloud and everything in the cloud is up always, right? Like, if you don't look at it, it's up, right? They don't look. So they're starting to just expect that it's always available because people tell them that it's going to be always available. And another big one is IT people don't like doing major IT tasks at 3 a.m. every Sunday. They want to be like sleeping or something like that, or not getting paged when things die. They don't want to do hardware maintenance tasks at convenient for users hours of the day. Current solutions. XF server connected to multiple application servers. Not really a solution. Still a single point of failure. You just have that one XF server sitting there and everyone's connecting to it and doing stuff. So the application servers can be brought down and back up again, and it doesn't impact users. But if anything happens to that XF server or the data that it's storing, everybody's down. And it might have performance problems depending on your access patterns. So if you were currently running on a system where the data and the logic are running in the same place, and you move to a system where you have application servers and XF server, without any application changes whatsoever, you might run into some performance problems there. And it still does not let you perform maintenance tasks on that XF server. So if you get a Windows update or a Linux update or whatever update, you can't bounce that thing without taking out all of your users. So that's bad. On to our next current solution, shared storage area network with cold standby. So if you have a storage area network, so big expensive disk array thing that's plugged into various servers through networking equipment, if server A, which is connected to that, goes down, server B is connected to it, it can be brought back up very quickly. Very little downtime, but you can only have one server attached to a given LUN at a given time. So you don't share a LUN between the two servers. You have to disconnect from one of the servers before you can bring up the other. So it's a cold standby. It's not hot and completely ready to go, but it's very little downtime if something has to happen with that one machine. It is a manual transition. This isn't automatic. No one is detecting failure. This is your IT person says, shut that one down, bring that one up. And they manually go do that through whatever processes they go about doing it. And it is still a single point of failure. That SAN, if the cleaning person goes by with their cart, pulls the plug accidentally out of the wall, your SAN is not doing anything anymore because it's not plugged in. So single point of failure, not ideal. Multiple SANs with synchronous replication. Now we're out of this single point of failure thing. Like, this is getting a little bit better. These things are kind of expensive. They require some pretty high-end stuff connected in between them in order to make this work. So ISAM flushing has to be turned on in order for these things to survive a hardware failure. Even if you do turn on flushing, it is still possible to corrupt an index. Notice I am actually just saying index now instead of data file. It's still possible to corrupt an index if it fails at just the right moment. If the buckets are getting shifted around in the index just as the power goes out, bad stuff happens, or the hardware failure, or whatever it is. It's not going to finish writing that index. When you write data files, they happen in chunks. They basically happen all at once. They're relatively atomic with modern hardware. So the data file would be safe in a flushed environment, but the index is too many moving parts. Still a manual switchover process. Your IT guy is doing this by hand. So if it's happening at 3 a.m. because something went wrong, there was a beeper and someone woke up and someone dealt with this problem at 3 a.m. Unhappy IT person, one way or another. It might be possible, if you throw enough money at it, to get this to replicate across locations. There's probably a distance limitation. No matter how much money you throw at it, you can only send the data so far without impacting your operational performance, but it is possible to replicate to another location. Very, very little, if any, downtime during a controlled switchover here. If you have web services, they stay operational. The people who are using those web services probably don't even know you switched from one machine to the other. SSH users who are connected in, or Telnet users, something like that, the server they were connected to went down. They need to reconnect, and whatever application state they had at the moment that it went down, it is gone. It's not persisted. They're not on that machine anymore. They are now connecting to a different application server. Has the same data, but if you didn't write that data to the shared disk, then you are not looking at what they were looking at before. RDP users, similar story. The application server goes down, the RDP session goes down. You got to reconnect. Whatever your application state was, it is gone now. XF server connections need to reconnect, and XF server plus connections need to reconnect. So everyone in that list has some disruption except for web services. Web services are the only way that you can get zero disruption, zero downtime for your users in an idealized environment. XF server connections in the future might not be quite this way. They might get better. We're hoping to make them optimistically better so that when one machine goes down, you reconnect to another and it reacquires positions and reacquires locks wherever possible. But that is not the case today. So, on to new. So, things that didn't exist prior to recently. This is doable in released versions of software. So, it's not like I'm announcing new features right now. This is just new use of the product that we haven't done in the past. So in Windows Server 2019, there is a thing called Storage Spaces Direct. That is not inherently new, but the features and functionality contained within it in 2019 are newly improved. They are better than they were before, significantly so. Entry into this space is cheap. You're just buying 1, 2, 3 servers of regular entry-level kind of hardware. They're not particularly specialized, although they can be. And that's your Windows failover cluster. It is strongly recommended to use RDMA hardware for your networking in between them. And the networking that is inside of your Windows cluster should be private to that cluster. Use separate adapters to talk to the outside world than what you talk to the inside of the cluster with. It keeps the traffic free of basically packet collisions, because you need guaranteed delivery that's really fast and low latency inside of the cluster in order to make all this stuff work well. So on the graph of what is best for performance, InfiniBand is better than RDMA over converged Ethernet, which is better than IWARP, which is better than Ethernet in terms of performance. So InfiniBand, really fast. Rocky, a little bit less fast, but still really fast. IWARP, also very fast. Ethernet, we all know how Ethernet works. In terms of ease of deployment, Ethernet's really easy. Everyone knows how to do it. Everyone's already got it. IWARP is the next one that's easy because it's just TCP/IP over Ethernet. And then Rocky is a little bit harder because you need to do things like data center bridging inside of your Ethernet sort of configuration. And then InfiniBand is same deal. You got to do data center bridging and you have pretty specialized hardware that you're using to do it with. Flushing improves reliability during hardware failure events. This may or may not actually be important to you. It depends on how big or small the transactions that you are processing are on a given moment, and what sort of failures you're anticipating dealing with gracefully, and what sort of performance degradations that you can actually live with in your production environment. The quorum, which is a fancy word for how you decide whether you need to switch over between not servicing requests on server A and only servicing requests on server B, is automatic. So you do not wake up at 3 in the morning to switch these over. It happens because the system understands how to come to a quorum. There is a minimum of 2 servers plus a witness. So if you have just 2 servers and no witness, how does server A know that it's dead? It doesn't. It does not actually know. If there's just 2 things in existence, server A can't tell if it can't talk to server B because it itself is dead, or if it's because server B is dead. So the witness acts as a tiebreaker to say, okay, server A, you can see the witness. You're the one who's actually alive. Server B can't see the witness, so it's dead. No more servicing requests for server B. Everyone goes to server A. Really, though, you should not deploy less than 3 machines in a cluster. So they will allow you to do it with 2 plus a witness, but you shouldn't do it. You should definitely do 3 or up. There's always got to be an odd number somewhere in order to be that tiebreaker. 2 plus a witness. You really want 3. Witness would get you to 4, which would mean you'd need a tiebreaker. So you always have to end on an odd number. So the third server here is the tiebreaker if there's something bad that happens between server A and server B. That's called split brain. If anyone ends up reading blogs about this in the future, the scenario I just described to you is called split brain. So yeah, three servers in a cluster is ideal. Or 3 or higher. You can go up to 16. There are 2 different ways you can use this. So the first way is active-passive. So it's a lot like that hot standby scenario that I described with the multiple storage area networks. So both machines could service requests at any given time, but we've decided only server A is going to handle things, and it's going to write data that gets persisted across the cluster, but only server A is actually going to handle requests. So it is active, and the other one is passive. You can switch between them at will, or if a failure happens, the switchover happens automatically. Disk activity is replicated synchronously inside the cluster. Only one machine is running the application code at a given time. This lowers lock contention in the cluster because there's only one machine and it's only dealing with locks within itself. So this can lead to lower latency for write or store intensive workloads. So if you're doing something like a massive day end, running that on all the machines in a cluster would be a lot more expensive from a lock contention perspective than doing just one machine running this process, changing everything. Controlled switchover for maintenance is simple and safe because it's controlled, so it doesn't matter whether you're flushing or not, you're going to give it enough time to actually do the switchover safely. You can schedule your maintenance during business hours, software updates, operating system updates, hardware updates and replacement, network infrastructure changes. They just do that. No one has to know that you brought down server A because you transitioned all the users onto server B or C or something like that. Bring it down, do whatever your IT people need to do, bring it back up, and let the users come back to server A. They have no idea that it even happened. Unscheduled maintenance, that's things deconstructing themselves when you didn't want them to, can be trouble-free. If a hard drive fails on server A, it doesn't really matter. You were writing to B and C, and so your data is still good. They drop out of the quorum and it stops servicing requests. Anything that was in flight to that server probably fails, but everyone else keeps operating exactly the way they were. And use web services. Obviously, for all of these things, the switchovers are completely seamless if you're using web services, and if you're using RDP or SSH or something like that, they're less seamless. So the next scenario that you can use is called active-active. So people in the VMS world, this is your clusters. We're just sort of catching up to you now, which is convenient for us now, but past us. So your disk activity is still replicated synchronously to other services or servers in the cluster. You run one instance of your application on each server in your cluster at the same time. Read throughput scales very well. I have some graphs, and I will show you guys actual numbers of what this did for us in-house. Write throughput actually scales pretty well. CPU, network, and RAM obviously scales like really well because there's no contention for RAM. You're just, here's more RAM to throw at your problem. Write speed goes down, or rather the latency required for each write operation increases if the file is being concurrently written to on more than one server. You can put up to 16 servers in one of these failover clusters and have them all running actively at the same time. You will need a load balancer of some kind. Generally speaking, someone else deals with that, right? Like there's a physical piece of hardware that you buy to do that load balancing, and you probably don't want to buy just one of them because you want to make sure that you don't have a single point of failure that's just a different single point of failure. But it's not a synergy thing. You buy a load balancer or two, you set them up the way the load balancer people say you're supposed to set it up, and it does its job and everyone's happy. But you need something to fill that job of load balancing. Stateless web services are an ideal fit for this environment. I keep saying it, but they really make your life so much easier if you're trying to deal with any kind of 24/7, 365 type computing environment. Everything works better there. Right. So I mentioned this a little bit in that shared SAN. So if you have to move data between two different data centers, you're going to need a really big network connection. There's two different ways you can do it. You can do it synchronous and you can do it asynchronous. And within the asynchronous, you can actually maintain the write ordering, which keeps your files from being corrupted. So if you're doing asynchronous, you need to maintain write ordering. But it basically just determines, is the data center that you're replicating to super duper right now live, or is it consistent but behind by 5 or 10 minutes, or 30 seconds, or 5 seconds? It depends on the size of your network connection. This is how you get actual disaster recovery as opposed to a hard drive lit on fire and the rack was safe, but that machine was totaled, right? Like for real disasters where your data center ends up under the ocean, this is the only way to solve that. There's a couple of different ways, even within that you can actually do your replication. So you can do cluster-to-cluster replication, where they're basically two distinct clusters, and you manually say, like, this one's live or this one's live. There's also a thing called a stretch cluster that does automatic versions of that. You will probably experience better performance in the manual switchover cluster-to-cluster environment, just because they're trying to manage some things for you inside of a stretch cluster that you probably aren't going to get much benefit out of. And those things that they're doing are not cheap. Where do you host these things? You can host them in the cloud. Azure definitely does this. AWS, not so much. It's possible to host these things in AWS or in Google Cloud, but they don't offer the right RDMA interfaces for Windows to do this job fast, essentially. So they do actually use really high-end networking gear inside of the AWS and Google Cloud infrastructure, but they don't expose it to you. You don't get to use that high-end networking gear. It just exists and they run on top of it. Whereas inside Azure, it peeks through and you actually get to use it yourself. So the other option is on-prem with a really big internet connection. A really big, really fast, really reliable internet connection. The other option is hybrid. So one data center can be in Azure, little bitty baby one could be in Azure, and then the real one that you use all the time can be on-prem. So you don't have to pay for two whole data centers worth of stuff. You pay for your emergency, like bad things happened to me this week and we need to scrape along and be alive while we figure out what we need to scale up. But it gets you there for the time being, and it costs you a lot less to own just a little bit of the cloud as your disaster recovery plan, right? It's an easy failover to it, and then as users come on, you scale it up and make it bigger. But it's for disasters. It's not for your day-to-day operations, so why do you want to basically spend full price on just this once-in-a-lifetime kind of failover? So hybrid can be a really good way, and ExpressPath is just the Azure name for how you get a really fast network connection between your on-prem data center and their data center. So there's a lot of management that you have to do when you're running a Windows Failover Cluster. Windows Failover Cluster Manager is built in. It's a desktop app, and it's being gradually phased out. They introduced it in, I think, 2008, and it is a little creaky around the edges. All the functionality still seems to be there, but they are deprioritizing it. You can do anything with PowerShell. PowerShell is magic. You can execute commands across your entire cluster with it. Every single piece of functionality that there is a GUI for, there is a PowerShell commandlet for that functionality. You can perform any operation inside Windows Failover Clustering or Windows Server in general. Any operation you can perform, you can do it with PowerShell. As a replacement for the Windows Failover Cluster Manager, they are now pushing the Windows Admin Center. So it's new in Server 2016, I think. It was like a intro beta thing in 2016, and now it's the way forward in 2019 onwards. It is browser-based. Your server is the web host for this browser-based application, and it's where they're putting all of their effort. So probably pick PowerShell or Windows Admin Center if you're like doing a new deployment of these sorts of things. How do I get one? So if I want to buy this stuff and I don't want to just DIY it, they have this thing called Azure Stack HCI. It doesn't really have anything to do with Azure. They just like branding everything Azure, I guess. Anyone notice that? It's Microsoft certified hardware solutions, but it's provided by other people. So they have a bunch of hardware providers that basically say, here's your cluster in a box, plug it in, it's a cluster now. Congratulations. And it deals with all of the networking equipment that's required and certifications thereof. So they are guaranteeing you that it will work as advertised. In terms of if you do want to do it yourself, you're feeling particularly adventurous, it's not that hard to get one running. It's inevitably going to be cheaper if you do it yourself, at least in terms of CapEx. And there is no certification safety blanket. So no one is going to say, like, I guarantee you this is going to work, A, and B, properly. Because there's a difference, right? Like, it can work and not work properly at the same time. The other option is Azure, which is on a per monthly basis stupid expensive, but it's really, really easy and it's very well supported. So disks matter a lot because what I'm going to start talking about is disk performance and read-write throughput and all of those sorts of numbers. And so I want to make really clear what the different levels of performance are that you can get. So Intel Optane DC persistent memory. That's like a RAM stick, but it's way, way, way freaking bigger in terms of storage capacity. It plugs into a RAM slot, but it's a hard drive. It's a really fast, individual byte addressable hard drive. It's unreasonably fast, it's very expensive, and it is not limited by PCIe bandwidth. So you can pump hundreds of gigabytes per second through these things. They are really, 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 really fast. It's basically like having RAM, but it's not RAM. Instead, it's a disk. Next one down in the hierarchy of hard drives is NVMe. So you just plug that sucker straight into the motherboard, and it's really fast, really not that expensive. Not for petabytes of storage, but I haven't seen petabyte size ISAM files yet, so I don't think you guys need that. But NVMe is a really good place to live in terms of how you store your data. SSDs, like the regular kind that you plug in with SAS or SATA or something like that, are next on the list. They're basically the same price as NVMe. They're slightly slower than NVMe. Their only advantage is you can plug an obscene number of them into the same server. Because you don't need an individual PCIe slot for each one of them, you can have a lot of ports on your host bus adapter and plug SSDs into all of them. And hard drives, please don't. Just don't. There's no reason to at this point. So don't buy spinning Rust platters. They are not great at all for anything, except Netflix streaming. So what to expect when you're expecting IOOPS? With flushing turned on, you can expect every operation that you perform to be taking 10 times longer to complete. That is not necessarily commentary on the total throughput, but for an individual request from start to finish, with flushing turned on, you can expect it to be 10 times slower. Without flushing, you can expect it to be 2 times higher latency. Again, this does not impact total throughput. If you increase the width of your requests, you will still accomplish the same number of things. But for an individual request, you're moving from 50 microseconds to 100 microseconds, right? Like, we're actually talking about very small numbers, but each one of them adds up and they are done serially in most of your applications. And so that's why I'm telling you the latency will increase. Without flushing, but with 16 concurrent operations, so basically you're servicing 16 different users at the same time, you can expect the total throughput to be pretty similar. It's not an order of magnitude slower, it's not 2x slower or anything like that. It's a little bit slower, but not by very much. And for read-heavy workloads, Active-active is actually the fastest you can get. If you're doing a whole lot of reading, the cluster is faster, right? Like it scales per machine you add in, right? There's no real additional cost for each of the readers. The costs are all associated with the writers. So read throughput and read latency actually scales very well. So this is our server. It's lovely, isn't it? They're basically old, disused servers that we had laying around that we went and bought a kind of expensive piece of network kit, which is the Mellanox ConnectX 4s that you see there. Those are 25 gigabit Ethernet adapters that support Rocky, which is, if you saw in that continuum, one of the really fast options. So we put the minimum number of hard drives in these things, which is 4. You have to have at least 4 hard drives because they don't want you having less than that because it would not survive failures if you had less than 4. We have a bunch of RAM in each one because that's what's in them. These are essentially pretty old hardware. They're like 2012-ish hardware, other than the network cards. Important caveats. Again, test servers, they're freaking old. They are severely limited in PCIe bandwidth. Those 25 gigabit Ethernet adapters have more bandwidth over Ethernet than the systems have between the processor and everything else in the system. Literally. Like those cards are faster than the motherboard in those servers. And everything is running off of that same bus. The cards are running off that bus, and the hard drives are all running off of that bus. So there are constraints there that will hopefully not be the case for any of you doing this out in the real world. Our test servers are not identical hardware. One of them has 6 cores and the other has 4. It's the hardware that we had, so it's what we went with. We are not using data center bridging. This is probably not a problem for us because we literally plug them directly into each other, so it's very unlikely to get packet collisions, but you guys would be using data center bridging in a real environment. It should have no impact on the way this test is running, but I'm letting you know so that you understand the actual configurations that we worked with. Our network connections are copper SFP28s, so they're not RJ45s that you would normally see plugged into the Ethernet. They're special thingies that are more expensive than that are frequently used for fiber optic runs, but that's what we're connected with. They're just regular copper. Our Mellanox cards are actually dual port, 25 gigabit. So the total bandwidth they're able to push is 50, but again, that's more than the total PCIe bandwidth of the system, so we just didn't even bother plugging both of them in. If you were doing this in real life with real hardware that had real PCIe bandwidth, you would plug both of them in because A, it's faster, and B, it's faster. So definitely plug both of them in. Our hard drives are low-end consumer-grade SSDs. Those are just Samsung Evos. They're not Pros or anything like that. They're 256 gigs, which is the slowest thing Samsung sells at this point. Size actually changes how fast they operate. And our HBA, host bus adapter, so where we get our SAS ports from, is already dramatically oversubscribed in terms of PCIe bandwidth of the network cards. Our tests were done using 16K stripes. So if you think about how RAID works, we are using 16K stripes for this test. And despite our normal performance advice about RAID setups, we experienced some counterintuitive performance increases when we switched to 256K stripe sizes. The numbers that I'm going to give you guys are actually still with the 16K, but there was unexpected slight performance bumps that were positive for 256K, so keep that in mind. So this is a graph of IOOPS for a single server, and it is write mostly. So we see pretty nice curves there that are relatively easy to predict. As we move colors there, so the light teal to like a purple to a gray to a different color purple, that is the number of concurrent operations that we're performing. So we go from either 1 all the way up to 8. So you can see as you increase the width, for the most part, we're kind of leveling off after 4-core CPUs being what they are, but we still actually increase a little bit as we go up to a certain point. So this is IOOPS of an active-passive write mostly. So it's the same set of operations that are being performed. It's the same number of threads from one to the other. But you can actually see that it's kind of jagged, and the flushing ones have literally fallen off the graph because they got 10 times slower. They were already significantly slower to have flushing turned on, but these things fell off the graph. But in terms of what the actual numbers are, notice we're at a peak of 80,000, or 800,000 rather, and we're at a peak of 400,000 for active-passive, write mostly. IOOPS for active-active, write mostly, this thing gets really jagged. A lot of this jaggedness is potentially solved by mitigating all of those PCIe things that I talked about and plugging both Mellanox cards into each other so that they have the ability to fire off extremely low latency requests more than one at a time. But you can also still see that we actually make it up pretty high, especially on that sequential store no flush that's all the way to the right. So we are still doing write mostly in all of these cases. In the sequential store case, the very few reads that we're doing are sequential, and the writes that we're doing are stores as opposed to updates. I was genuinely not expecting this result for updates versus stores because store does more operations than update does. I know this for a fact. I know that that's how it's actually operating. But then when I look at the performance data, I can also see for some reason it's faster to do more things than it is to do less. I don't understand that, but that is what the data is that we have. And when I say write mostly, I mean one-to-one. So we are doing one write per read. So very, very write heavy. I suspect very few of you in this room do anything like that for your general processing. Maybe things like day ends, month ends, year ends, whatever would do something similar to this, but even then, one-to-one is a pretty extreme ratio for reads to writes. So here's IOOPS for a single server read mostly. So this is 1 to 1,000. I actually have the data for everything in between 1-to-1 and 1 to 1,000, and I can share that with anyone who's particularly interested, but it's basically a trend line, so it's not terribly helpful to know what happens in between that trend line. So again, we see the IOOPS graph for single server. It's very pretty. The things level off exactly where you expect them to do, right at that 4 cores, because that's how many we have, mark, and then it grows a little bit beyond that. And we are hanging out in the 400,000 IOOPS per second range. So in active-active, and I've actually skipped active-passive here because it provides us with almost no interesting information, read mostly is really, really, really fast. So the peaks on these graphs are in that 600,000 range, and even when we're flushing, they're well above the 100,000 range. So you can do a lot of I/O operations, even on super freaking old hardware that has not been actually configured by a real IT manager that knows what they're doing. Because I configured them. I'm not an IT manager. But the point here is these are the kinds of I/O operations you should be able to expect at least, kind of a baseline. If you're doing a lot of reads, you're going to have a good time. Like, this is great for you. If you're doing all writes, which I don't think anyone is doing here, then it's a different question, and you probably need to dig in deeper to your specific workloads, whether this is right for you. If you're somewhere in between, we're increasingly thinking this is a really, really, really good pathway for people to go down. It's fast, it's industry standard, and it's not that hard to configure. So what does this not help with? So what I'm saying what setup I made does not help with. Crashes in the middle of a transaction. If you are performing a day end and you don't have transactional support via like Harmony Core or something like that, and your transaction fails because it crashed, like software bug, crashed transaction halfway through, you will have written half of your data and not the other half. We will have dutifully persisted this half data that you have written, but this does not roll back your operation just because you threw an exception in user code. So this doesn't fix that. Killing processes with the task manager. This does not fix that. Please don't do that. It's bad for the health of your files. Don't kill processes with task manager. This is true for people on Linux too, even though this discussion is not actually about Linux. Please don't kill your processes with an equivalent of task manager. It's not healthy. Cosmic rays that strike your non-ECC RAM. We don't help you with that. We would recommend you put actual ECC RAM in your box so that cosmic rays can happily strike your RAM and no one will be the wiser or care about it. This will not help you if an admin accidentally deletes all of your files. Please back up your data at regular intervals. This is not a replacement for backups. This is high availability. You still need to have backups for if something goes horribly wrong with your data and you need to restore that data to your highly available servers. This backup stuff can be coordinated using software like Veeam and the SYN Backup VSS service. That is an unannounced product that will be going out in version 11 that allows you to coordinate your backup software to prevent ongoing Synergy IO transactions to ensure that your backup software is collecting actual, valid, clean ISAM files that are not partway through a transaction. So it's automatic, it runs in the background, it makes life better if you're using backup software. We like Veeam, it's what we use in-house, it's what we've tested with the VSS services. VSS, by the way, is not our acronym, that's Microsoft speak for backup service provider. Not all VSS backup providers are created equal. Some of them like to disallow correct operation unless you pay them enormous sums of money for their enterprise variant. Veeam doesn't do that, and so we like Veeam. But if you're using the semantic variant of backup software, essentially only works properly if you pay for the enterprise version. Otherwise, it does not do what's advertised. If you don't replicate to a separate location using that stretch cluster or the multiple clusters, you are just one flood, fire, or earthquake away from downtime. So this doesn't help with that. This is just a single rack. They're plugged in directly to each other. So don't lose the rack. You can bring down and up individual machines. You can lose power on individual machines, and it will survive all of those things. But if your entire rack is submerged or lit on fire, your software will not be running. Do I have to use Hyper-V? I didn't really mention Hyper-V at all in this, but do I have to use it? That's what we did. So the key technology here that actually enables this, that VMware does not provide, is called SR-IOV. So that is single route IO vectoring? I think it's vectoring. And it is available on most server hardware made after 2012. Our super old 2012 hardware has this in both cases. VMware supports SR-IOV, except you can't move VMs inside of your vSphere cluster thing with VMware. And IT admins really like to move VMs around. It's kind of like the thing that they really care about in terms of doing this stuff. You can live migrate machines inside of Hyper-V that are using SR-IOV. The reason why SR-IOV is important is because without it, you are interacting with a ridiculously fast network card at a very, very high cost per operation you interact with it at. So that thing can, by itself, natively, raw, literally push millions and millions of packets per second without using any CPU, unless you run it through virtualization. And then all of that fastness and that expensive card you just bought, like, it's basically a normal card. Normal Ethernet. Don't even bother. It's not going to be fast. You need SR-IOV or to be using it raw as an actual card that's plugged in running on the machine. One or the other, that's what you need. PVRDMA is VMware's official way to do this, but it doesn't work on Windows. So it's not really a good way for doing Windows failover clustering at all. So yeah, if you end up talking to VMware people, that's their answer, but it doesn't help you. So Hyper-V is our strong recommendation here. What about Linux? For all of the people in the room that use Linux, things like Ceph might work. We don't know. They look like they should work. We have not invested in testing them. We're still investing in the Windows failover cluster side of things, and there's a fair bit more effort that we want to put into making sure that that experience is good for everybody. We do suspect strongly that Ceph will have much lower performance for our use cases, basically just because of the way they are architected, and they are not operating system level, their user space. Operations are going to be more expensive. And we strongly suspect that you will have to turn on flushing in order for Ceph to not corrupt your data. Basically, Windows gets to cheat a whole heck of a lot because they are the operating system, whereas Ceph is just a bolt-on, right? You're just running this thing. It's just a user space file system. It doesn't know anything about buffers that are being kept around inside your application that are unflushed, so they don't get to cheat the same way that Microsoft does. If you find yourself interested in trying that out because you're like, I really need clustering on Linux and I need to try this right now, go for it. Please try it. We will give you the programs that we use and the procedures we use to validate on Windows. And feel free to do that on your own cluster and report back to us and all the other customers that this was terrible and it was the worst, or dang, this stuff is like sliced bread. Throw some butter on it. Either way, maybe somewhere in between, not sure. Please report back if you do, though. And also very important, Rev 6.1, Steve has talked about this. Rev 6.1 in ISAM, it's new in version 11. It adds support for adding indexes on the fly, which is important for 24/7 computing. It supports rebuilding the index on the fly, again, important for 24/7. It is a requirement for data file only flushing, which improves our performance when we're doing flushing, which, as you could see from those graphs, is very expensive. So it's really nice to have any performance improvements we can get. It detects when an index file is out of sync with a data file and allows you to automatically correct that, which is a lot more likely to have happen in a hardware failure type scenario inside of a cluster. And it dramatically improves the rebuild and conversion performance. So these things matter, although they are not required for you to use Windows failover clustering. So that's that. Here's some additional materials about failover clustering in general. That's the Pluralsight course that I use to learn how to set up our cluster. It's very comprehensive and it tells you all sorts of stuff. It's kind of long, but it is very good for this sort of conversation. There's some Channel 9 videos that I've linked here as well that are very good from Ignite, and the general link for Azure Stack HCI. So they collected all of the hardware vendors that are certified for Azure Stack HCI, and you can like go buy whatever the hardware is or forward that link on to your IT people to say like, oh yeah, I need to get one of these. Could you please acquire one? So that's that. All right. Thank you.